Hi, section 2.6, limits involving infinity. In part 1, we'll study horizontal asymptotes, and in the second part, we'll consider oblique and vertical asymptotes. Let's see this example. It is showing a graph of a function y equal x squared minus 1 over x squared plus 1. As you can easily verify here, if x approaches minus infinity, then function values approach 1. And if x approaches infinity, then the function values become closer to 1. As in this example, some functions have limits as x approaches minus infinity or plus infinity. Let's see this intuitive definition. F is defined on some interval a to infinity. Then we can say that when f can be arbitrarily close to L for x sufficiently large. And this limit can be made various ways. For example, the function values can approach from below and or from the above, or here oscillatory way. However, the function values are approaching L. So in this case, we say limit of f as x approaches infinity is L. Now we define the limit at infinity formally. Fx has the limit L as x approaches infinity, and we write in this way: if for arbitrary epsilon positive, there exists a corresponding number m such that whenever x is larger than m, then fx and L, the difference, is bounded by epsilon in modulus. So that is a formal definition. So it is a sort of epsilon delta argument. There's no delta. However, anyway, for arbitrary epsilon, you should be able to find number m such that this inequality is satisfied. Okay, here the same way, and similarly, when x approaches minus infinity, we can define the limit of the function as x approaches minus infinity. Now, here we have a definition. Y equal L is called a horizontal asymptote of the curve if as x approaches infinity or minus infinity, the function value is approaching L. Either way, at least one side, we have a limit, and then we can say that the limit in the horizontal line is called horizontal asymptote, because the asymptote is not really the function value all the way, but anyway, function values are approaching to the line. In this case, oscillatory, so that it's the same, and here many points. However, anyway, not all the way they are the same. Okay. In this example, let's find the limit as x approaches infinity or x as approaches minus infinity. As you can see here now, once x is approaching minus infinity, then function values are close to 0. And also the right side, as x approaches infinity, the function values again are close to 0, so that we can say that y equal 0, 0 is the limit, y equals 0 is horizontal asymptote. Okay. Let's try to evaluate the limit or show that limit doesn't exist. Okay. Once you have such a problem, then if you try to plug infinity, then the numerator and denominator, the simultaneously become infinity. So this fraction is shape of infinity over infinity. In this case, the strategy is here dividing the numerator and denominator by the highest power of x in the denominator. That means that right now in denominator, highest power is x squared. So we'll try to divide in top and bottom by x squared. Then, okay, now the given term is the same as limit. Okay, x goes to infinity. Now we divide the top by x squared. Then the first one will be 6, and second one will be 8 over x, and last one will be 3 over x squared. Now bottom, we also divide the bottom by x squared. Then first term will be 3, and the last term will be 2 over x squared. Now when x approaches infinity, then we can easily see that this term will approach 0, and again that term approaches 0, and again that, so that we can here that is approaching 0, that is approaching 0, again this approaching 0, which means that here that is approaching 6 over 3. As x approaches infinity, it happened, so that is 2. So we can say that is horizontal asymptote. As x approaches minus infinity, the same will happen here. The function value approaches 2. Okay. Find the limit. Same way. For this fraction, now highest power in the denominator is x minus 2, x to the minus 2. So we divide by x to the minus 2, which means multiply x squared. Okay, so given term is the same as limit. Okay, we multiply x squared, top and bottom. Then there is x, now there is x minus 2, and x squared is multiplied, so there is 1. Now x squared multiplied, so that is x to the minus 1. As x approaches infinity, we know this will approach 0, and again that one. But here, so the bottom is around 1, but top is becoming larger and larger, so that it will blow up. So the limit is infinity, but infinity is not a number, so that there's no limit. Now, for this problem, okay, and third power is a continuous function, so that now limit and continuity are commutative, so that you can apply this limit inside, and later on you can take third power. So let's start with this way. Limit x approaches minus infinity, and then x squared plus x minus 2 divided by 8x squared minus 3. Again, the largest power in the bottom is x squared, so that you can divide top and bottom by x squared. Then that is 1 plus 1 over x minus 2 over x squared, and divided by 8 minus 3 over x squared. And as x approaches minus infinity, and except 1 and 8, everything else will approach 0, so that the limit will be here now 1 over a. So here from given term, and that is now, okay, 1 over a and for the power. So the answer must be half. Okay. Okay. We want to evaluate the limit. Okay, for this one, if you apply limit, then first term will go to infinity, and also second term is going to infinity, so that the shape is infinity minus infinity. So it is not easy to determine the limit. The way to solve this problem is just multiply, conjugate, so rationalize. Okay, so that g, the given term, is same as limit, same limit as x approaches infinity. Now we are multiplying its conjugate. So the square root of x squared plus 1, now minus x. Okay, its conjugate is square root of x squared plus 1, now plus x, divided by, here on the bottom, we have to put this one, and square root of x squared plus 1 plus x. Okay, now it is same as limit, and a minus b, a plus b shape, so a squared minus b squared, which is x squared plus 1 minus x squared, and divided by the same denominator. Okay, now this is same as a limit, and 1, okay, let's see the detail, the square root of x squared plus 1, now plus x. So here, top is limit 1, but bottom becomes larger and larger and larger, so that the limit must be 0. Okay, now part B, we want to find the arctangent and 1 over x minus 2 as x approaches 2 from the right, so that x minus 2, x is larger than 2 and approaching 0 is basically larger than 0. X minus 2 must be larger than 0, but here that is approaching 0. So that, and this 1 over x minus 2, so 1 over x minus 2 is approaching 1 over 0 plus, which means that is blowing up infinity. So the given term is same as now tangent inverse arctangent. We can say that now we can here now limit and x approaches 2 plus and 1 over x minus 2, and this value becomes larger and larger and larger, and approaching infinity. So we can say that is now pi over 2. And tangent has a value increasing to become infinity when the angle is approaching pi over 2, so that the answer must be pi over 2. Okay, for this problem, the same way, but x is approaching 2 from the left, so that 1 over x minus 2. X is now smaller than 2, but approaching 2, so that that one is approaching 1 over 0 minus, that is minus infinity, becoming the infinity in negative direction. Okay, so here the given term is same as basically tangent inverse, arctangent minus infinity, we can say in this way, which is same as minus pi over 2. Okay. The tangent, graph of tangent is given in this way. Okay, in xy coordinates, and go to minus infinity, and here given that way. Here when x equal pi over 2 is going to infinity, and x is minus pi over 2, then it's going to minus infinity. Okay, that is graph of tangent, so that is inverse with minus infinity must be minus pi over 2. Okay. Okay, now let's try to find the limit. As x approaches infinity, and we easily see that 1 over x is approaching 0, so that now limit can be applied first. So it's the same as here now sine and 0, so that is 0, quite simple. Okay, for part B, once x is approaching either side, and now x times sine 1 over x. Sine 1 over x is approaching 0, but x is approaching infinity. So that here infinity times 0 shape, so it is not easy to decide. Okay, so to handle the problem, we try to use new variable, which is a sort of a change of variable. Then now given term can be written in this way. T, rather than 1 over x, we can put t, and rather than x, we can put 1 over t. And x approaches plus minus infinity is the same as, now once x is approaching plus minus infinity, then now t is approaching plus minus 0, so that here the given term is the same as that. But we already know that limit as t approaches 0, sine t over t is 1, so the value is now 1. Okay, that is final answer. The approach direction doesn't matter. T approaches from the right or from the left, it doesn't matter. There's sine t over t has a limit 1, so the final answer is 1. Okay, now that means that we didn't say here the asymptote, but anyway, for this problem, the asymptote, the horizontal asymptote is y equal 1. Okay, that is horizontal asymptote. Okay, now for this example, and we'll try to find the horizontal asymptote of the graph of that. And that is the same as finding the limit, as so that we have to apply limit as now x approaches plus infinity, and also limit as x approaches minus infinity. Okay, let's begin with that one first. So the limit x approaches infinity and f of x. Then that is same as now limit, same limit, and here the function is square root of 4x to the 6 plus 1 divided by now 2 minus x cubed. Okay, we may try to put x to the 6 outside. Now x is approaching infinity, which means that x is positive, so that here it'll go out x to the 3, x cubed can go out. So okay, so limit, and 2 minus x cubed is the bottom, and top is now x to the 3 and square root of 4, okay, x to the 6. Now, so that we have to divide the inside this radical by x to the 6. So that becomes 4, and the last term should be 1 over x to the 6. Okay, now here we try to divide the top and bottom by x cubed. Then that is a limit, and square root of 4 minus, okay, 4 plus 1 over x to the 6, and this is here 2 over x cubed and minus 1, right? So once x is approaching infinity, then these two terms will approach 0. So remaining terms are, and now square root of 4 and minus 1. Square root of 4 is the same as now 2, so that will be minus 2. Okay. Now how about the other side? So here limit x approaches minus infinity of f of x. Okay, the same as here this case, but now in this case x is approaching minus infinity, so x itself is smaller than 0, so that here you have to be a little bit careful. Rather than x cubed, you have to put here x cubed and absolute sign and square root of 4 plus 1 over x to the 6 divided by now 2 minus x cubed. You have to be careful because x itself is negative and x cubed is also negative, but you have to put yes, absolute value, positive value. That is exactly happening when you are dealing with here, for example, square root of x squared is not the same as x. In fact, it's the same as absolute value of x. But here we didn't put absolute sign because x is positive. Now, once x is a negative, then you have to make it reflection, which means that that portion is the same as, in fact, minus x cubed. So we can write once more, limit. Okay, that is minus x cubed, and square root of the same inside of this radical, and that is 2 minus x cubed. Now we can divide by x cubed, then we can reach here limit and minus square root of the same thing inside, and this is 2 over x cubed minus 1. As x approaches minus infinity, the inside, that is 4 plus 1 over x to the 6, this term and that term will go to 0. So that here minus square root of 4, which is minus 2, divided by minus 1, so that must be 2. Okay, so as x approaches minus infinity, the function value is approaching 2, and on the right side, the function is approaching minus 2. So we have two horizontal lines, y equal now minus 2 and y equal 2. These two are horizontal asymptotes. Okay. Okay, for that problem, again the same way, and okay, limit. So that x is approaching, for example, here, plus minus infinity and f of x. If we consider this way, then now this f of x can be written in this way. Here, there is x cubed minus 2 over, okay, we eliminate x, the absolute sign, x cubed plus 1 when x is positive. Now, when x is negative, then that is x cubed minus 2 divided by minus x cubed plus 1 when x is negative. So that that for right side we are using that one, and for left hand side we are using that one. Again, from this one, once divided by x cubed, then this will become here 1 minus 2 over x cubed divided by 1 plus here 1 over x cubed, and the other side x, okay, again divided by x cubed will make here now 1 minus 2 over x cubed divided by now minus 1 plus 1 over x cubed. So as x approaches infinity or minus infinity, the value is approaching now here 1, and this value is approaching now minus 1. So we have y equal 1 and y equal minus 1, two horizontal asymptotes. So that these are horizontal asymptotes. Okay? Okay. Now, we want to evaluate the limit for this one. We already considered this function, but let's do again. Here, x is approaching to 0, then from the left hand side, then 1 over x itself is now, this is smaller than 0 and approaching 0, so that it's approaching from left hand side, so that 0 minus, which means there's a minus infinity. So that here the given term is same as e to the minus infinity, which is 0. Now for the other part, if x is approaching from the right, then 1 over x, that is approaching to, okay, x is positive but becoming 0, so that is approaching from to 1 over 0 plus, which is infinity. So that a given term is e to the infinity, which is infinity. Infinity means it's becoming larger and larger and larger. Okay, so that is infinity. Okay, now what if we consider the case x goes to now minus infinity? How about that? Okay, once it is happening, then 1 over x is approaching 0, so that here e to the 1 over x is approaching now 1. Okay. Now, if x is approaching infinity, then again 1 over x is approaching 0, so that here e to the 1 over x is approaching now 1. Okay, let's try to make some graph sketch of that function. Okay, now in xy coordinates, okay, there is x-axis, there is y-axis. Once x is approaching 0 from the left, then the value is approaching 0. Okay, so it is from left is 0, but when x approaches minus infinity, then it's approaching 1. So it looks like here, that is now function value looks like moving that way. Okay, so that is here now 1. Now on the right side, the function value goes to infinity when x is approaching from the right, so that value will be large around there. And then x becomes larger and larger and larger, then the function is approaching 1, which means that the graph must be given in this way. So here, y equal 1 is the horizontal asymptote. Okay, so that is a sketch of the graph for y equal e to the 1 over x. Okay, we want to find the limit as x approaches 0 from the right for this x times 1 over x, the greatest integer function. Okay, now if you consider greatest integer function, then it is given in this way. So that means that, for example, now here, if you are considering, so this blue part is the same as y equal t greatest integer. Okay, let's see some detail. Once t is between 0 and 1, then if t is around here, then greatest integer, the integer smaller than equal to t is 0, so that the function value is 0. And once t becomes 1, then greatest integer must be 1, so that it has a jump. And t is between 1 and 2, then the greatest integer is 1, so that the function value is constantly 1. And once t becomes 2, then the greatest integer must be 2, so that jump up here. So in this way, the graph can be made. Now, rather than t or x itself, we are dealing with here 1 over x. Okay, so and then x is approaching from the right. So that portion is approaching infinity. And so it is not easy to handle as it is. So we try to use change variable. T is 1 over x. And then x is approaching from right, from the right, 0, so that here 1 over x will be, okay, is approaching 0, so that it is approaching infinity. So here t is larger than 0 and approaching infinity. Okay. Now, along with that change variable, here that whole thing is changed into limit, so that given term is changed into now, rather than x, t goes to infinity, and then x will be 1 over t, and here inside this sign, which will be 2. Okay, we reset that one. So here we analyze a little bit for that term, and this function is always bounded by t and always larger than or equal to t minus 1. More precisely, as you can see from the graph, that is always larger than t minus 1. You can see here there's no overlap. It's empty, so always larger than t minus 1, but also this inequality is okay. Okay, now along with this inequality, if we multiply 1 over t, then the left low bound becomes 1 minus 1 over t, and upper bound will become 1. So that this term is basically between here 1 minus 1 over t and 1. Now we can use a sandwich theorem. When t goes to infinity, this term will approach 0, so that bottom and top simultaneously approaches 1, so that the limit must be 1. Okay, that's the end of part 1. I'll see you in the second part. Thank you.